and we start our lecture 26. So first section for today, 26.1, is an application of Taylor's theorem, and that is Extremum criteria. So here we'll formulate the following theorem. Suppose f has continuous as derivative on AB. N is an even, that is very important, integer x naught belongs to the interval AB, and f prime at x naught equals to second derivative, and so on up to derivative of order n minus 1. All of them are zeros, but the last nth derivative is not zero. Then, first, x naught is a point, is a maximum point if and only if nth derivative at x naught is negative. Second, x naught is a minimum point of f, of course, of f. Minimum point if and only if nth derivative is positive. There are two possible rules to remember the correspondence between maximum and the sign of derivative. One is emotional, so emotion like that means we have a minimum, and like that maximum, what corresponds to the sign. Another is so imagine there is a rain on the blackboard, and what happens with water? If it's like that, we have the water, positive amount of water, and if it is like that, we have no water, so negative amount of water. These are two possible rules to remember the correspondence between the sign of derivative. Also, most often the case of n equals to 2 is used, of course. First derivative is 0, second derivative is not 0. But it doesn't matter, it's valid for an arbitrary even integer. That's important. So, proof. Let x belongs to a neighborhood of the point x0, which is in our interval. We can always find such a neighborhood because the interval is an open set, so for arbitrary point x0 of our interval, we can find a neighborhood which is in the interval, is a subset of our interval. Okay, then f satisfies all conditions of Taylor theorem, namely we have nth derivative which is defined on a neighborhood and x is in that neighborhood, hence there exists a point C in between, let me write it like that, in between x0 and x, such that we have f of x equals to Pn fx Taylor polynomial plus n minus 1 plus nth derivative at c over n factorial times x minus x0 power n. So we apply Taylor's theorem not for n but for n minus 1. Now, what is about Taylor polynomial for our function? The Taylor polynomial, which is n minus 1th Taylor polynomial, which was defined like that, what is it? Look at the condition. All derivatives starting for k equals to 1 up to k equals to n minus 1 at x0 are zeros. So then only one term which is not 0 maybe is for k equals to 0. So it means we have just f of x0, nothing else remains. Okay. Then, so it follows from those conditions that f of x minus f of x0 equals to nth derivative at c over n factorial times x minus x0 power n. Now, I'll consider only the case 1. Second possibility is considered quite analogously. I will not do it. So, we have in fact two assertions here in both sides. So suppose x0 is a maximum point. Then there exists a neighborhood. Okay, let it be some different maybe. I didn't indicate which neighborhood before, so let it be delta naught of x naught, such that for all x from that neighborhood, by the definition of maximum, we have f of x less or equal f of x naught. That is by the definition of maximum. So there exists a neighborhood such that for all x from that neighborhood, we have inequality f of x less or equal f of x naught. Now look, for all x from that neighborhood, what we have? So we have this part is non-positive. Now here n is even. Hence this is non-negative. So it means from this inequality, from those two in fact, it follows that nth derivative at C should be non-positive. But this is valid for arbitrary x from that neighborhood, right? So once x approaches to x naught, what happens with C? C was in between x naught and x, hence C approaches to x naught as well. And because of continuity of nth derivative, then, so it follows from this nth derivative tends to nth derivative of x naught as x tends to x naught. And from this inequality, what follows? We can deduce that nth derivative at x naught is non-positive. And since we suppose it is not zero, so it is negative. And this part is proved. This part is proved. Now, converse. So here we suppose nth derivative is negative, but also we know nth derivative is continuous at x naught. Hence, by properties of continuous functions, there exists a neighborhood b delta 1, let's say, x naught, such that for all x from that neighborhood, we have nth derivative at x also is negative. Now, we apply again Taylor's theorem, right? Now for x's from that neighborhood. And look at the final equality. So C is also, if x is here, then C from that Taylor theorem is also in that neighborhood, right? So it means nth derivative is negative, and since this is non-negative, the product is non-positive. And this is valid for arbitrary x from a neighborhood, hence x naught is a maximum point. So the converse assertion is proved as well. And let me remark that in fact x naught is a point of strict extremum. So the inequality here is strict once x does not coincide with x naught. Right? Okay, so let's apply that theorem. So consider an example. Example. F of x equals to x squared cosine x. So let's investigate that function to extremums. So we find the first derivative, it's 2x cosine x minus x squared sine x. And we can see that f prime at 0 is 0. Next, look at second derivative. Second derivative is 2 cosine x minus 2x sine x and 2x sine x from here. 4x sine x and minus x squared cosine x. So we see second derivative at 0 is equal to 2, and that is a positive number, and the order of derivative n equals to 2 here. So we apply the theorem for n equals to 2. So n equals to 2, x naught is 0, right? And we see that look, second derivative is positive. It means that 0 is a minimum point. So x naught equals to 0 is a minimum point. Of course, the question of other extremum point is essentially more complicated for that function, because we cannot solve in explicit form the equation cotan x equals to x over 2. It's impossible, but okay, so one extremum point is clear. And yeah, in fact, we can notice that this local minimum equals to 0, right? So f of 0 equals to 0. But this is not a global minimum, since f of pi equals to minus pi squared, and it is less than f of 0. So that is a minimum point, but remember, we consider only local extrema. So the function is in fact positive only in a diluted neighborhood of 0, but not everywhere. Okay, that was the first section for today. Now, as one application of Taylor's theorem. Now, second application is about asymptotic expansions. So, So 26.2 asymptotic expansions. So what are asymptotic expansions? In fact, we will not consider asymptotic expansions in general, like they will appear in many areas of mathematics, in many other mathematical disciplines, maybe later. So, the example of asymptotic expansion was Taylor formula with remainder in piano form. So let me recall, we had such an expansion. What means expansion? Just a minute. So so what is the expansion? The expansion is, so we have f of x naught. I am writing down what means Taylor polynomial, plus f prime at x naught over 1 factorial times x minus x naught power 1 plus second derivative over 2 factorial x minus x naught squared, and so on up to nth derivative at x naught over n factorial x minus x naught plus or small of x minus x naught power n as x tends to x naught. That is an example of asymptotic expansion. So it means that if you consider the behavior of our function as x tends to x naught, then if we decide that it is possible to forget about functions which tend to 0 faster than x minus x naught to the power n, so they are very small from our point of view, then from that point of view we can replace our function by this polynomial. So asymptotic expansion means that because of some goals you can forget about terms, let's say, which contain larger powers. And the problem to find asymptotic expansions, okay, here we were interested in asymptotic in X, but also very often there are sequences of functions, and it is interesting to find asymptotics of those sequences depending on n for arbitrary x and so on. So these are very important questions in many applications of analysis. And you see that this is an example of an expansion of this form. Plus little o of x minus x naught power n as x tends to x naught. So general form of expansions of such a kind is like that. And in fact, such a kind of asymptotic expansion is unique, and we can prove it just now. So that is a theorem which is called just uniqueness. So, okay, let me theorem 1, uniqueness, no more theorem in that section, uniqueness of asymptotic expansions. Okay, suppose that two asymptotic expansions f of x equals to a naught plus a1 x minus x naught a n x minus x naught power n plus little o of x minus x naught to the power n as x tends to x naught, and f of x equals to b naught plus b1 x minus x naught plus so on plus a n x minus x naught to the power n plus o small little o of x minus x naught to the power n as x tends to x naught. Okay. Then that two asymptotic expansions and these are valid. Then a naught equals to b naught, a1 equals to b1, and so on, a n equals to b n. So once we have an asymptotic expansion, it is unique. Proof. Okay, so let us find the limits. So limit as x tends to x naught f of x. Since we have such an inequality as x tends to x naught, we know little o tends to 0 even faster than this, and this tends to 0 as well. So you see that all terms except for the very first, tend to zeros. So it means that from the first expansion we have the limit equals to a naught. From the second it is equal to b naught. So both are equal because of uniqueness of the limit. Now let us rewrite our expansions like that. So f of x minus a naught over x minus x naught. From the first expansion we can write, what is it? So we move a naught to the left hand side and then divide by x minus x naught. Then this is a1 plus so on plus an x minus x naught power n minus 1 plus little o of x minus x naught power n minus 1 as x tends to x naught. Analogously, we can proceed with the second expansion. So, and okay, I can write like that. And now little o of x minus x naught to the power n minus 1 as x tends to x naught. And then we observe that b naught equals to a naught. We have proved it, right? So the right hand sides have limits as x tends to x naught. Hence the left hand sides also have limits and they are equal. So limit as x tends to x naught, f of x minus a naught over x minus x naught exists. And it is equal to, simultaneously, to a1 and b1. So they're equal to each other, a1 and b1. And we can proceed further and further in this way. So maybe so it means that now we can subtract, so move, let's say, a1 to the left and then divide by x minus x naught. So we can write f of x minus a naught over x minus x naught minus a1 over x minus x naught equals 2. And now that is a2 plus so on plus an x minus x naught to the power n minus 2 plus o small o little o n minus 2 as x tends to x naught. And analogously we can write for the second, taking into account that a naught and a naught equals to b naught and a1 equals to b1. So I can write analogously same expression is equal to, from the second asymptotic expansion, that one, little o of x minus x naught to the power n minus 2 as x tends to x naught. And once again we can take a limit of right hand sides as x tends to x naught. So right hand sides have limits, hence left hand sides have limits as well. And since left hand sides are equal, it means that, okay, I may rewrite as f of x minus a naught minus a1 x minus x naught over x minus x naught squared. This limit exists and it is equal simultaneously to a2 and a2. So we can proceed by induction. Once we have proved that a naught equals to b naught and so on up to, let's say, a m equals to b m, right? So if we suppose this is like an induction hypothesis, then we can write f of x minus a naught minus so on minus a m times x minus x naught power m over x minus x naught power m plus 1 equals to a m plus 1 plus so on plus a n x minus x naught power n minus m minus 1 plus little o of x minus x naught to the power n minus m minus 1 as x tends to x naught. And analogously for the second asymptotic expansion, we can write analogous equality. And left-hand side are equal, so we can take limits of right-hand sides, because limits of right-hand sides, they exist, obviously. So it means the limits of left-hand sides also exist, and they're equal because left-hand sides are equal from the induction hypothesis, and hence limits of right-hand sides are equal, and they're precisely a m plus 1. So a m plus 1 equals to b m plus 1. And we can do it up to the power n, So this is the end of the proof. So it means that there is only one asymptotic expansion of such a kind, if it exists, of course, if any, right? And as a corollary, we observe that if the function has n derivatives up to order n, and it has asymptotic expansion, then coefficients should be expressed like we did. Of course, we don't need this corollary, since now, in fact, we know that once the function has all derivatives up to order n at x naught, it automatically has asymptotic expansion, which is given by Taylor's formula with remainder in Peano's form, little o, that one, right? So once you have the derivative of nth order at x naught, then you have such a asymptotic expansion. But as you see, for the existence of, let's say, a2 and b2, you need only the existence of such a limit. You don't need the existence of second derivative. And in fact, we'll consider an example just now. Okay, let's have a break. actually. Okay. So we continue, and I would like to give an example which shows the difference between asymptotic expansions and Taylor expansions. So, example 1 for that section. Consider the function f of x equals to x cubed sine 1 over x as x not equals to 0 and 0 as x equals to 0. Obviously, we have asymptotic equality little o of x squared as x tends to 0. Why? Because if we divide, so limit as x tends to 0, f of x over x squared equals to the limit as x tends to 0, x times sine 1 over x after cancelling x squared. And we have a product of infinitely small function, x tends to 0, times a bounded, hence that is a 0. And that is, it means the expansion is like that, right? So it means that in our asymptotic expansion from the theorem, a naught equals to a1 equals to a2 equals to 0. And n equals to 2, right? So we wrote asymptotic expansion, this asymptotic expansion, for our function as x tends to 0, up to quantities of second order. But let's try to compute the first derivative. So, okay, for x not equals to 0, it's easy to compute. 3x squared sine 1 over x. In fact, yeah, x cubed plus x cubed times cosine 1 over x times minus 1 over x squared. Or we can rewrite it as so 3x squared sine over x minus x times cosine 1 over x for x not equals to 0, right? And we can find the derivative at 0. So derivative is at 0. We can find by the definition, that is a limit as x tends to 0, f of x minus f at 0 over x minus 0, and that is a limit as x tends to 0, x squared sine 1 over x, and that is 0. So f prime of x is well defined. We can write it here. Sine 1 over x minus x cosine 1 over x as x not equals to 0, 0 as x equals to 0. But if we'll try to find the second derivative at 0, so yeah, f of 0 also is 0, and that is a1, oh sorry, a naught equals to 0, f prime at 0 equals to a1 equals to 0. Here, no problems with respect to Taylor expansion, but the second derivative at 0, if it exists, equals to the limit as x tends to 0, f prime of x minus f prime at 0 over x minus 0. So if we substitute the expression for the derivative, it gives limit as x tends to 0. So divide by x, 3x sine 1 over x minus cosine over x. And this limit doesn't exist. Why? Because you may consider a couple of sequences. Let's say xk equals to 1 over pi over 2 plus pi k, k natural, right? Then limit as k tends to infinity of xk, k tends to infinity, so it's 0. But limit as k tends to infinity, if we substitute those values, xk's, 3xk sine 1 over xk minus cosine. So here I don't want to substitute what is xk, but over there it's better to substitute. 1 over xk will be pi over 2 plus pi k. So what is it? Cosine pi over 2 plus pi k is 0, and there is 0, so we have 0. But if we consider another sequence, let's say xk tilde equals to 1 over 2 pi k, k natural, then again the limit as k tends to infinity, xk tilde equals to 0, but the limit of the values here, 3xk tilde sine 1 over x k tilde minus cosine, and here I'll substitute it and we have 2 pi k. Cosine 2 pi k is 1, so here again we have limit 0, so we have minus 1, and it means the limit doesn't exist. So second derivative doesn't exist. So you see, we have asymptotic expansion for our function f of x with a0, a1, and a2, which all are equal to 0, but only a0 and a1 are connected with values of the function and its derivatives. a2 is not connected because of not existence of second derivative at 0. So it means this is an asymptotic expansion, but not a Taylor expansion. Okay. Now, let us compute main asymptotic. It will be not a theorem, but it's very important, so maybe table of Maclaurin expansions, Maclaurin expansions of elementary functions. So there are two main asymptotic Maclaurin expansions. Here all of them are Maclaurin will prove it. So first one, e to the power x equals to 1 plus x squared over 2 factorial, x power n over n factorial plus o of x, little o of x power n as x tends to 0. Second, sine x minus x cubed over 3 factorial plus minus 1 to the power n, x to the power 2n minus 1 over 2n minus 1 factorial, and plus 1 then here, and plus 1, and plus little o of x to the power 2n as x tends to 0. Third, cosine x equals to 1 minus x squared over 2 factorial minus 1 to the power n plus 1 x to the power 2n. No, here I should put n. 2n factorial plus little o of x to the power 2n plus 1 as x tends to 0. Fourth, logarithmic function x minus x squared over 2 minus 1 to the power n plus 1 x power n over n plus little o of x to the power n as x tends to 0. And the last one is binomial expansion. 1 plus x power alpha equals to 1 plus alpha x plus alpha times alpha minus 1 over 2 factorial x squared plus so on plus alpha times alpha minus 1 so on up to alpha minus n plus 1 over n factorial x to the power n plus little o of x to the power n as x tends to 0. These are main expansions which are necessary to remember. Of course, there are more, but all others you can easily deduce. Yeah, in fact, you can deduce also sine and cosine from e to the power x, of course, and logarithm from binomial using some results. Okay, so let's prove those expansions. So, proof for those expansions. The first one. So, we know that derivative of exponential function is this exponential function itself. Hence, doesn't matter how many derivatives we take, we still have the same exponential function. So it means that for f of x equals to e to the power x, we have f of 0 equals to f prime at 0, and so on, equals to nth derivative at 0, that is e to the power 0, and that is 1. So all derivatives exist, and by Taylor formula with remainder in Peano form, we'll obtain that expansion immediately, right? Okay, second. Here we know the formula sine x and derivative equals to sine x plus n pi over 2. Then it means that for n equals to 2k, we have, for f of x f of x equals to sine x. We have f at 0 equals to second derivative as 0, and so on, equals to the last derivative of 2k. That is, yeah. So if we have 2k here, then we have x plus kp over 2, that is sine n equals to kp, and that is 0. And for n equals to 2k plus 1, we have f prime at 0 equals to f fifth derivative at 0, and so on. So all derivative of for m plus 1, let's say, at 0 equals to sine of, if we substitute for m plus 1, it gives sine of 0 plus pi over 2 plus 2m pi, and that is 1. And third derivative equals to seventh derivative, and so on, f for m plus 3 at 0, sine 0 plus pi over 2 plus 2m pi plus pi, and that is minus 1. And it gives the expansion. So you see, first derivative is 1, third derivative minus 1, and so on. We have alternating of signs. It gives sine minus 1 to the power n plus 1, and again by Taylor's theorem with remaining Peano form, we will obtain that asymptotic expansion. Third expansion is quite analogous. I will not consider it. So let's deduce fifth expansion. Fifth. So what is n plus 1 plus x power alpha nth derivative? Okay, I'll not suppose alpha, so alpha is not natural. Otherwise it will be 0, starting from some. But in fact, we need not to put this restriction. So once we differentiate every time, or maybe I'll consider step by step. So first derivative alpha times 1 plus alpha, alpha minus 1. So second derivative is derivative of this expression, and that is alpha times alpha minus 1, 1 plus x power alpha minus 2, and so on. So after many applications of differentiation, we have alpha times alpha minus 1, so alpha minus n plus 1 times 1 plus x to the power alpha minus n. So if alpha does not belong to n, the exponent, the power, will be never 0, and it means that for f of x equals to 1 plus x to the power alpha, we have nth derivative at 0 is equal to alpha times alpha minus 1, so on, alpha minus n plus 1. And in fact, this formula is valid not only for alpha not natural, but also for alpha natural, because once alpha is natural, sum of those products will be 0, and all derivatives become zeros. So this restriction is not necessary anymore. Okay, so, and once we found the expression for nth derivative at 0, we deduce immediately the fifth formula from Taylor theorem with Peano's remainder. And let us write down particular case alpha equals to -1. So 1 plus x power -1, by this general formula we can write 1 minus x plus -1 times -2 over 2 factorial x squared plus so on plus -1 -2 so on minus. So if we put -1, we have the last minus n over n factorial x to the power n plus little o of x to the power n, and that is, we have here -1 to the power 2, here -1 to the power n. So 1 minus x plus x squared so on plus -1 to the power n x to the power n plus little o x to the power n, x tends to 0. This is also useful to remember, but you know this expression up to little o from formula for infinite geometric progression sum. Okay, so that is for 1 plus x minus 1. Then consider, so now I can prove fourth formula. And how we may proceed here. So we consider logarithm 1 plus x, and we observe that derivative is equal to 1 over 1 plus x, that is 1 plus x minus 1. What it means? It means that if we consider the function f of x equals to logarithm 1 plus x, then nth derivative at 0 equals to derivative of 1 plus x minus 1 of order n minus 1 for x equals to 0. And we know what is it. We computed it. That is minus 1 to the power n minus 1 times n minus 1 factorial. Minus 1 to the power n minus 1, n minus 1 factorial. Right? Then, once again by Taylor's theorem with remainder in Peano's form, we obtain, so f of 0 also I need f of 0 is 0, of course. So we start with coefficient. Let me write coefficients. So n equals to 1, we have just 1 over 1 factorial x. Then n equals to 2, we have minus 1 factorial minus 1 factorial over 2 factorial x squared, so on, and minus 1 to the power n minus 1, n minus 1 factorial over n factorial x to the power n plus little o of x to the power n as x tends to 0. And you see that, okay, what we have after cancelling factorials, minus 1 to the power n minus 1 over n. And that is precisely, okay, here we have n plus 1, but it doesn't matter. It gives precisely fourth formula. Now, and so it means these are indeed Maclaurin expansions. And these are also asymptotic expansions, of course, but let me formulate, once again emphasize the difference between asymptotic expansions and Maclaurin expansions. So, example 2, find asymptotic expansion for f of x equals to sine x over x, x not equals to 0, 1 as x equals to 0, up to near x not equals to 0, up to x to the power n. So now it's easy. We write sine x equals to x. Okay, look at the, I'll not rewrite second expansion. And divide by x, we obtain sine x over x equals to 1 minus x squared over 2 factorial plus so on plus minus 1. So what was written there? And plus 1, I wrote plus 1. And plus 1 over 2n minus 1 factorial x to the power 2n plus little o of x to the power 2n plus 1. Wait a minute, I stopped there up to 2n minus 2n minus 2 is not very good, but let it be. 2n minus 1 as x tends to 0. Yeah, and that is asymptotic expansion. But imagine that I would change the question. So instead of asymptotic expansion, replace Maclaurin expansion, right? Then this would be not the end of the solution. Why? Because Maclaurin expansion means that function has all derivatives up to order 2n minus 1. And the only way to check that this function f of x has such derivatives is to check that it has all derivatives at 0. And this is not an easy task, in fact, right? So, for example, for f prime at 0, how we proceed? Just by definition, the only way. X tends to 0, f of x minus f at 0 over x minus 0. It gives limit as x tends to 0 sine x over x minus 1 over x. That is limit x tends to 0 sine x minus x over x squared. We can use L'Hopital rule. X tends to 0 cosine x minus 1 over 2x. Once again, L'Hopital rule. X tends to 0 minus sine x over 2, and that is 0. So now we have the first derivative, so f prime of x equals to, okay, if we differentiate sine x over x, we obtain x cosine x minus sine x over x squared as x not equals to 0, and now we computed x equals to 0. Then we should proceed further and further. So second derivative and so on. So, okay, in fact, you can find a general representation for nth derivative like a trigonometric combination of trigonometric functions with algebraic polynomials, and somehow it is possible to prove that indeed that function has derivative of arbitrary order at 0. And that is very, very long problem. So you see, find asymptotic expansion is very easy, but Maclaurin here it is really difficult. Really difficult. Okay. Now, how it works, those asymptotic expansions. So, that is, in fact, the maybe this, okay, I'll write firstly in general and then an example. So, use it, okay, let it be example 3. Suppose f of x equals to, let's say, am x to the power m plus o of x to the power m, x tends to 0, and g of x equals to bn, x to the power n plus little o of x to the power n as x tends to 0, right? So we have two asymptotic expansions of this form, and find limit as x tends to 0. Yeah, of course, I should also suppose am not equals to 0 and bn not equals to 0. So find the limit f of x over g of x. So how we compute it? So we need to consider several cases. The first most interesting case, n equals to m. In this case, we can write limit as x tends to 0, f of x over g of x equals to limit x tends to 0, am x power m plus little o of xm over bm x power m plus little o xm, because n equals to m. Divide by x power m both numerator and denominator. It gives am plus o of 1 over bm plus little o of 1. What is little o of 1? That is something what tends to 0 as x tends to 0. So it tends to 0, and the result is am over bm. Okay, other cases, let's say m less than n, then the limit x tends to 0, f of x over g of x, if we proceed in analogous way, divide by x to the power m smaller degree, we obtain am plus O1 divided by bn x to the power n minus m. Here n is greater than m, plus little o x to the power n minus m. And now you see, numerator tends to am not equal to 0, and denominator tends to 0. So the result is okay. That is I would say that is infinity without sign, but we have no infinity without sign, plus infinity and so on. So yeah, rigorously speaking, the limit might not exist, right? Because we don't consider infinity without sign. That is okay. The question if there is infinity with sign or not depends on the behavior of denominator. And for the case m greater than n, it's easier. Limit as x tends to 0, f of x over g of x equals to the limit as x tends to 0. Here we divide by smaller degree x to the power n. We obtain am x to the power m minus n plus little o x to the power m minus n divided by bn plus little o of 1. Now the denominator tends to be n, which is not 0, and numerator tends to 0, so the result is 0. Yeah, to avoid this problem, yeah, that is a question, but the limit as x tends to 0, g of x over f of x is equal to 0 for sure. That is without any problem, right? But for f of x over g of x, we may have a problem. Okay, now how it works. Oops, it seems. Okay. But it makes no sense. Maybe the best idea would be to consider, yeah, I think next lecture will be devoted to finding of limits with the help of asymptotic expansions. So this example is more logic for next section, of course. Yeah, okay, but doesn't matter. I considered it today, no problem, right? Okay, I have no possibility to consider any example, and that's all for today then. Thank you.